Okay, so this is your free body diagram practice worksheet for, that you're supposed to be working on. I'm just going to go over the first couple problems just so you know what your work should look like. Again, if you have a printer, you can print out this worksheet. If you don't have a printer, then you can do this work on a scratch sheet of paper. Please make sure that you write your name on the paper and that you label the question numbers. Okay, so let's read what the question or what the directions say. It says draw a free body diagram for each object. Be sure to include the net force. If the net force is 0, indicate that symbol right there means sum of the forces. You can just write out F net equals 0. Okay, so for all these problems, you're either going to write F net equals 0 or F net does not equal 0. Plus, you're going to draw an FBD. Okay, so take a look at question number 1. Question number 1 says a box is pulled along the ground by a string at a constant velocity against friction. Okay, so here's my dot representing my object. I'm listing out the forces that I know have to be there. Force of gravity, just because the box is not in space. I run through my mental checklist in my head that I have because I took good notes over the forces, and so I know in what situations I have different forces. And if you don't remember, you can always pull that PowerPoint up because all my PowerPoints are linked on my Canvas homepage. Okay, so let's think about this. Is there a rope or a string? Yes, that means there is a force of tension. Okay, is there a surface? Well, it's pulled along the ground, so that means yes, there is a surface. Is there friction? Yes, because, well, it says there's friction in the problem. Alright, so I go to draw my FBD, keeping in mind that if it's being pulled at a constant velocity, that automatically tells you that the net force is equal to 0 because of Newton's first law. Remember, an object in motion remains in motion unless acted upon by a net force. So if it's moving at a constant velocity, that means the net force on the object is 0. So I draw my arrows. Force of gravity going down, normal force going up, opposite to the surface or perpendicular to the surface. Balancing out the force of gravity. Notice how those two arrows are the same length. Okay, now which way is it being pulled? Well, it doesn't tell me, so I'm going to make up a direction. Let's say the string is pulling the box to the right. I draw FT going to the right. And because it's constant velocity, because the net force is equal to 0, I have to draw the force of friction the same length going in the opposite direction. Okay, and so that's what number 1 should look like. Let's take a look at question number 2. It says a rocket-powered sled accelerating, there's a context clue, from rest on ice. Alright, so here's my dot. I list out the forces. I always start with FG. I run through my mental checklist. Is there a rope or a string? No. Is there a surface? Yeah, because it's on ice. Okay, that's a surface. Is there friction? No, probably because it says it's on ice. There is a force from a rocket, though, and that's not one of the common forces I told you about. So let's just call that F rocket. Alright, force of gravity is going down. Normal force is going up. The fact that it's accelerating, by the way, that means that the net force is not equal to 0. Remember back to the first law flowchart, there's only 3 possibilities. If the net force is 0, that means the object is either at rest, or if it's moving at a constant velocity. And the third possibility is that it is accelerating and changing its velocity. So because it says it's accelerating, that automatically means the net force is not equal to 0. And so, which way is the rocket going? It doesn't tell me, and so I'm just going to make up a direction. Let's say F rocket is going to the right. And when I look at this FBD, Fn and Fg are going to cancel each other out because they're the same size in opposite directions. And then F rocket is unbalanced, and so there's going to be a net force to the right, which is why the rocket is going to accelerate. Okay, so pause there if you need to look at that, and then I'm going to go down to 13 and 14. Okay, so this should give you an idea of what these questions should look like. It shouldn't be super difficult. This should be pretty easy to complete. There's no calculations or anything, but you need to make sure that the labels are correct, that the lengths are correct. Don't just randomly start drawing like arrows going every which way. I always see people drawing like 4 arrows, you know, one going up, one going down, one going left, one going right, and like it. You have to draw the free body diagram based on the situation. Not every problem has 4 arrows. Some have 2, some have 3, some have 1. Okay, so keep that in mind. Alright, and then question 13 and 14. This section down here is a little bit different. It's giving you the FBD and asking you to describe the motion of the object in words. Anytime you're asked to describe the motion, that basically means is the object at rest? Is it moving with constant velocity? Is it accelerating? And indicate the direction of the net force. If there is more than one possible description, give both. So when I look at 13, I look at the FBD. There's no labels on the forces, but that doesn't matter. I'm looking at the direction and the size of the arrows. I have one arrow going up, one arrow going down. If I were to add those together to get the net force, those two forces would cancel out. That means that the net force here is going to be 0. Alright, what does that mean? Well, that means there's two possible descriptions. Either the object is at rest, or it's moving, but according to the first law, the only way it can move is at constant velocity. Okay, so that's what 13 should look like. Okay, and actually I'm going to show you 16, because 14 is pretty easy, but 15 and 16 are a little trickier. Okay, so I'm going to erase this so I can scroll down. Okay, so take a look at 16. 16 says the object is initially moving to the left. Now you might look at the FBD and be like, oh wait, isn't it moving to the right? No. Remember, a free body diagram does not show you which way an object is moving. It only shows you which way the forces on an object are acting. Okay, so when I look at this FBD down here, I have a force down, a force up. If I add those together, they're going to cancel each other out. But the arrow to the right is longer than the arrow to the left. Now what that means is that the net force is not equal to 0. In fact, the net force is to the right. Now, what does that mean? Does that mean the object is moving to the right? No. In fact, it tells us the object is moving to the left. What that means is that the velocity is to the left, but the acceleration is to the right because the net force is to the right, and therefore this object will slow down. In the last video I said this before, but if velocity and acceleration act in opposite directions, the object is going to slow down. If they act in the same direction, like in 15, I'll tell you right now, if the object is moving to the right and the net force is to the right, that object is going to speed up. Okay, but that would be for 15. For 16, it's moving to the left, but the net force is acting to the right, which means the velocity and the acceleration are going in opposite directions, and this object will slow down. Okay, so this object is accelerating. Specifically, it's going to slow down, but it's going to keep moving to the left. It's just going to slow down. Alright, so there are 4 problems done for you. Okay, this worksheet shouldn't take you all that long. As always, please let me know if you have any questions. And I'll see you guys in the next video.